Hello, Namaskara, ಎಲ್ಲರಿಗೂ. I am Professor P.R. Ampivoli, Professor in the Department of Mathematics, KLS, Gupta Institute of Technology, Belagavi. We are doing under VTU E-Shikshan, the third semester Engineering Mathematics 3, Module 3. We have dealt Fourier transform. This is my class number 7. Today we are dealing with Z transforms. So in the beginning, let us have some introduction part of Z transform. Fourier transform was for continuous functions, whereas Z transform takes care of discrete phenomena, and this also has a lot of applications in signals and systems, in communication theory, in electrical circuits. So let us see what is the basic introduction of this. See, Laplace and Fourier transforms. Dear students, no harm if you start writing along with me. Many times I have told you, please be ready with your pen and paper. These two and many play an important role whenever the system is continuous system. Important role in the so-called analysis of continuous type of structures or continuous systems we can write. Whereas this Z transforms, what happens is definitely very important. Okay, plays its role in the analysis of discrete phenomena or discrete systems. Many names we can use. So this is a mathematical tool where whenever we have got some discrete phenomena, we can use it. So this is also useful, definitely useful in communication theory. In communication theories, signals and systems, such as etc. Now let us observe what we know. Suppose Laplace transform of 1 is 1 by s. Laplace transform of t is 1 by s square. Laplace transform of e raised to 2t is 1 upon s minus 2. What we are observing? Laplace transform of sine of at is a by s square plus a square, and so on and so forth. What is happening? See the dear students, left hand side we have t domain. Left hand side we have got t domain. Right hand side we have s domain. In technical language, the same thing are known as time domain and frequency domain. But these are all continuous functions. For every continuous function in Laplace transform, what is happening? For every continuous function of the form f of t, many functions may be there. So here all are transformed to f bar s via either Laplace transform or Fourier transform. But how about this discrete systems? Okay. Similarly, very similarly, for every for a discrete system or function, we can call for discrete function. For continuous function, I call it as f of x or f of t, something notation. I am always telling you that notations are important. For discrete, we shall denote it by un, and let us get used to this. What is un? Getting used to a notation is very important. Discrete system function in n, say. Instead of function, I can use system, word system. Say I denote it by discrete function, say I denote it by un. Let us denote it by un. And a function, suppose in variable z, say I denote it by some function of z, u of z. Okay. There exists a connection between these two. Z transform as a connector. So I am giving the analogy of Fourier transform. Every t function, say here some t square, you transform to 2 by s cube. Object, its reflection. Okay, if you change the object, the reflection will change. Similarly, for discrete system, for every n function, we have got some z function. So let us see what are some n functions first. Let us observe some n functions. Okay, some functions in the variable n. Which type of functions? Discrete functions in n. For example, suppose I write un equal to, suppose, n square. Then here we take n equal to 0, 1, 2, 3. That is what is u0, n equal to 0, u1, u2. We generate integer values of n and so on. Go on putting n equal to 0, 1, 2, 3 here. 1 square, 2 square, 3 square. So this set generates some n values. In general, for un, which is given, there is n square. Let us observe some second function. Suppose I am having un equal to some 2 raised to n, 3 raised to n, some a raised to n, something like a equal to 2 raised to n, 3 raised to n. Then what are the values of u0, u1, u2, u3? Let us see. So what are the values of u0, u1, u2, u3? In this case, a raised to 0, a raised to 1. Go on putting n equal to 0, 1, 2, 3 here. A raised to 2, a raised to 3. In general, a raised to n. So what we are observing is, for every integer value n, starting from 0, positive integer n, we have got some u value which is generated because of these generators, or we call it as discrete functions. So let us go for one more. Suppose un is some cos of n theta, where n is 0, 1, 2, 3. So what are the different values of this u0, u1, u2? Cos 0 theta, of course it is 1. Cos 1 theta, cos 2 theta. So go on putting n equal to 0, 1, 2, 3, cos 3 theta. In general, n. One more? Why not for one more? Let us go for one more. Suppose un is n cube into a raised to n. So go on putting, what is the first value for u0 is 0, 1 cube into a raised to 3. Go on putting n equal to 2 here, 1 square, n equal to 1, 1 cube a raised to 1, n equal to 2, 2 cube a raised to 2, n equal to 3, 3 cube a raised to 3, and so on. So what we observed is, for every n equal to 0, 1, 2, 3, we have got particular discrete values. There is no value between 0 to 1, 1 to 2. It is taking jump. That's why we are taking calling it as a discrete system. So what we observed, what are the types of un functions? It may be n square, n cube, cos n theta. For n equal to 0, 1, 2, 3, we are generating some real number values. Real number values, that is very important. So now, all these n functions, question is, what is the question? All these n functions we have to convert in terms of z functions. How we convert? How we convert n functions to n functions to z functions. N functions to z functions. So let us see how we convert. Convert means you have to make mathematically a tool, make a ready tool and convert it. So now suppose I want to convert, suppose a un is there, some un is there, say un equal to suppose a, okay, un equal to a raised to n. Now what we do here, multiply, two operations I do, multiply by z raised to minus 1. This is the first operation. So what happens when you multiply by z raised to minus 1? This becomes a raised to n, z raised to minus n. For n equal to 0, for n equal to 1, n equal to 2, z raised to minus n. You'll go on getting different values. All those values, all values you should go on adding. Next is add all values for n equal to 0, 1, 2, 3. That is, you take summation of all such values for n equal to 0, 1, 2, 3. So here we have a small assumption. This un becomes 0 for n less than 0, n equal to minus 1, minus 2, minus 3. In the definition, we are heading towards definition. So what happens? We get, what happens? This is, carefully see this, this is getting converted to this via this operation. This operation itself we call it as transformation, or this operation itself we call it as transformation or z transform in this case. So what we got exactly is, after multiplying, un has changed to, a raised to n has changed to a raised to n, z raised to minus n, and we are adding all these for n equal to 0 to infinity. Whatever the function of z we get, that will be something in terms of z. So are you not curious exactly what function of z we are going to get? So corresponding to t function in Laplace, there is one s function. Corresponding to n function in z transform, there is one z function. So let me solve your curiosity. So this, after transformation, this u of z I am talking, this u of z is looking like this: a raised to n, z raised to minus n, summation n equal to 0 to infinity, go on putting n equal to 0, n equal to 1, n equal to 2. So a square, z raised to minus 2 means z square, n equal to 3. Are you getting reminded of some geometric series? And we have heard of a geometric series. If it is in the shape of 1 plus r square plus r cube, then we write it as 1 upon 1 minus r. Here this is our r. This is our r. Hence, given a raised to n function, we convert it to z function 1 upon 1 minus r. R is a by z, 1 minus r is a by z. So this is a z function. With little effort of simplification, with little effort of simplification, we get a nice z function, in this pattern, z upon z minus a. So indirectly you found, I can call it a z transform of some n function which you defined by multiplying by z raised to minus n and adding nothing but z by z minus a. So what you observed, observation is important. N function here, so n function here and corresponding z function here via multiplication is first operation, adding is second operation. Multiplication, adding. So we multiplied, added. At last, after some simplification, we got z function. Why not we should bundle it? Whatever the discussion is there, why not we should bundle it in terms of a definition? But before that, what I did, once again, summary of observation. Given a un function, convert it to some u of z function via some transformation known as z transformation. So two operations we did in z transformation. One, multiplication. So we are forcibly bringing z variable, multiplication by z raised to minus n, and then is important, and then adding all terms n equal to 0, 1, 2. We assumed that this un is 0, n less than 0. So why you multiplied by z raised to minus n? Need not multiply by z raised to minus n. If you multiply by z raised to minus n, you will get z transform. You can multiply by some other multiplier and add with different notions here. You will get your transform. You can define your own transforms. Why not try your own transform? Now we are ready to define what is z transform. So you should be able to write the definition of z transform. If un is a discrete function, with n equal to 0, 1, 2, 3 and so on, and assumption un equal to 0 for n less than 0, then the z transform, right, capital Z, little big z, not only capital, little big font z transform of this un function. In Fourier transform, what is to do? Fourier transform of x function, convert into f bar s. Now what we are going, n function to z function. Instead of Fourier transform, z transform. Like that there are many number of transformations, Laplace, Fourier, Hankel, Violette transformations, many. Z transform of un denoted by u of z, u of uz, or I can write this uz afterwards, denoted by z transform of this n function should end in some z function. So what are the operations in between? Carefully see it. To this n function, this is how the definition is framed. A z function is multiplied. You can choose your own z function. These are known as kernel of transformations. And multiplying and adding. But only positive integers we are adding. So this function we get. So one example already we have seen. Now we shall see many more examples. So this is provided some conditions we put, provided Infinite, this generates infinite series. Infinite series should not give you infinity values. It should be realistic values. Infinite series converges to some finite value. Also, see here n function to z function via z transformation. So here to here. But from here to here, how to get? That we call it as inverse z transformation. So this is known as z transformation of n function. So reverse, this is known as inverse z transform of z function. Also we call un as inverse z transform of u of z and denote it by z inverse of any z function comes back to n function. So dear students, we are there here to learn both z transform and inverse z transform. And in general, wherever there is a transformation, if there is no inverse transformation, then it is not useful. Laplace is there, Laplace inverse should be there. Fourier is there, Fourier inverse should be there. Because wherever object is there, we take the image. Domain to codomain we go. So we have to come back to domain. Whenever there is an encryption, there should be decryption. So without inverse transformation, definitely they will be not of much use. So here we observe some standard Z transform, some standard Z transform. But to observe that, we need a property. Okay, we need a property. But I will prove this later on. First, I will utilize this property. The property tells that first observe it. Okay, first we shall observe and bundle it as a property. Suppose I want to find the Z transform of n square. I can connect it to the Z transform of n raised to 1. So Z transform of n square is connected to Z transform of n raised to n. Via the connection, if you differentiate this with respect to z and multiply by minus z outside, both will be equal. If it is 2, it is 1. Z transform of suppose n cube. N square you should take to this Z transform. This becomes a function of z. You differentiate this with respect to z, multiply by minus z. One more, Z transform of n raised to 4. I think some of you can write minus z differentiation of Z transform of n cube. In general, instead of 2, 3, 4, I can put it as 1 also. In general, instead of 2, 3, 4, I can write theorem for p equal to 0, 1, 2, 3, for p equal to 0, 1, 2, 3 and so on, Z transform of n raised to p can be found using the Z transform of n raised to p minus 1 via the procedure of differentiation and multiplication by minus z. So this will be using at present. Proof we shall come back to that later on. So now, next example you observe. We proved that before the definition we proved, do you remember? Z transform of a raised to n. Do you remember? I will show you that Z transform of a raised to n was z upon z minus a. If it is 2 raised to n, z minus 2, 3 raised to n, z minus 3. Now I'll use that. If n equal to 0, z transform of a raised to 0, which is z transform of 1, is z by z minus 1, and 1 can be taken as z transform of n raised to 0 also. So we make use of this n raised to 0 concept. We make use of this n raised to this n raised to 0 concept. Using this n raised to 0, I find z transform by n raised to 1. So first example for you, find the z transforms of, so quite important. Okay, if you remember the previous this part, this is quite important. If you remember this, you can find all these examples. Find the z transform of un equal to n raised to 1, un equal to n raised to 2, un equal to n raised to 3, un equal to n raised to 4, and this start becoming the base of z transformation. So we are converting n functions to z functions. First one, see carefully, to find the z transform, to find the z transform of un, to change the z transform of n, what we do here, n raised to 1 is there, we take n raised to 0 and z transform of n raised to 0, we differentiate and multiply by minus z. So what we are going to get? Z transform of n raised to 1. We shall get used to this by one or two examples. Minus z d by dz of. So what is this z transform of? What is the z transform of n raised to 0? Z transform of n raised to 0, just in the previous step we found. Here it is. So this z transform of n raised to 0, z transform of n raised to 0, you substitute this here. So z by z minus 1, here I have to substitute z by z minus 1, bring this z by z minus 1 here. So let me write that part whichever I have marked as z by z minus 1. This is equal to minus z. You know the differentiation of quotient function, z minus 1 whole square, z minus 1 as it is. Differentiation of z with respect to z is 1, minus z into, again differentiation of z minus is 1. Z and z getting cancelled. This minus 1 becomes plus 1. So we have found with little simplification, z transform of n raised to 1, denominator, if this is 1, it becomes raised to 2 here. This becomes z by z minus 1 whole square. Let us go towards z transform of n square now. Now we know that this is minus z d by dz of minus z d by dz of, instead of n square here, you have to put n raised to 1. Now z transform of n raised to 1 is here. So this you have to substitute here. So let us write that minus z d by dz of, so whatever I have marked this bundle here, this I have to keep it here now. Okay, z by z minus 1 whole square. So with little effort, if I differentiate that, what I am going to get? Z minus 1 raised to 4, z minus 1 square as it is, differentiation of numerator 1, minus z into differentiation of denominator 2 times z minus 1. So with little effort, if you simplify this, I will not fall into simplification, much simplification. See, one of the z minus 1 factor, one z minus 1 factor you can cancel with the denominator. So minus z minus 1 whole cube, if you cancel one of the z minus 1 factors, you are left with this part. Again, with little simplification, we get minus z into z minus 1 whole cube, z minus 2z, okay, z minus 2z, it is minus z, minus 1. So shall we write the final answer? Z transform of n square. At last you found Z transform of n square. You found it as. So there is a method to remember. Minus becomes minus into minus plus. All the terms are plus. Z square plus z upon z minus 1 whole cube. Very similarly, we can prove that. Please try this. Z transform of n cube. If it is 2 here, it will be 3. If it is 3 here, denominator will be 4. In that way you can remember. But numerator I am giving you at present, but you have to simplify and see 2 times z square plus 4z plus 1. And that of z transform of n raised to 4, denominator no problem, something raised to 5, and that is z minus 1. How you write this z transform of n raised to 4? So if it is z cube plus 4z square plus z. If it is 2, this start from 2. If it is 3, it start from 3. If it is 4, it start from 4. Starting is 4. Then go on, decrease it. So now in between we have got 11, again 11, only coefficients I am telling, then 1. See how the coefficients are there. Let us observe. I will write it as a table. We proved today these things. Z transform of a raised to n is here. This side I am writing. This side I am writing un function. This side I am writing u of z function is z by z minus a. Z transform of 1 you found. Okay. So on left hand side I am writing un functions. On right hand side I am writing u of z functions. We proved this as z by z minus 1. Then we went on proving for z transform of n square, n cube and n raised to 4. So all these n functions, see once again I am telling this z is not a z variable, just like Fourier transform symbol. This is a symbol. This is a symbol z. This is a symbol z. Symbol z transform, just like Laplace transform L. This is a symbol. Unless until we understand the symbol properly, we can't write. So z of n. First of all, z of n was z by z minus 1 whole square. So here you have to understand the pattern. Dear students, this word pattern is very important. So once we understand the pattern, our thinking process becomes a little fast. Second one, for 2 it starts from 2 here, power z square plus z divided by z minus 1 whole cube. For 3 it starts from z raised to 3 plus 4z square plus z divided by z minus 1 raised to 4. For raised to 4, it start from 4. In between 2 times 11 and 11 will come. 11 and at last 1. Denominator is always whatever the power is there more than 1. So function is z minus 1 raised to 5. So let us observe all these 4. Whatever we have written, it will be. So let us observe all these 4 things. So first one was, second one, third one, and fourth one. Here, whenever there is power 1, it is 2 here, power 2, 3 here, power 3, 4 here, power 4, 5 here. And only thing is you have to remember these coefficients. Here coefficient is 1, here coefficient is 1, 1, 1, 1, here 1, 4, 1, here 1, 11, 11, 1. So remaining you can see, if you close this, you can write z by z minus 1 square. Denominator no problem. Whatever is there, the power is 1 more than that. Here start from 2, z square plus z, z cube plus 4z square plus z, raised to 4, z raised to 4 plus 11z cube plus 11z square plus z. Like that you can remember 111, 141, 111, 11, 1. You remember mobile numbers of many of your friends. Like that you can remember these also. So these are the main Fourier transforms we found. So let us write some examples using z transform of a raised to n equal to z by z minus a. So let us get used to this. A equal to 2, 3, 4 minus 1 by 3, 2 I write. What is z transform of 2 raised to n? What is z transform of 3 raised to n? What is z transform of minus or 3 by 4 raised to n? What is z transform of root 2 raised to n? What is z transform of, what is what is z transform of minus 3 by 2 raised to n? So let us write the z transforms of all of these. Like this you should get familiar to new language of z transform. So left hand side all n functions, right hand side I am writing corresponding z functions. It is nothing but coding, decoding only. Here to here we are coding. In this z language work will be simple, so that this is a time domain, this becomes a frequency domain. So if you see this previous one, wherever only a I am changing here. So wherever a is there, simple changes are being done. So instead of a, we have got 2 here. Shall we write instead of a, 2 here? So you have to write 2 here, z by z minus 2. This becomes z by z minus 3. This becomes z by z minus whatever is there here. So whatever is there here. Okay. So we are writing z transform of, so I was telling whatever is there you have to write. So we are writing z transform of 3 by 4 raised to n, so that just like 2 is z minus 2, 3 z minus 3, 3 by 4 is z by z minus 3 by 4. Can you tell me similarly, what is this? Z by z minus 2, whatever is there, root 2. Z by z minus, if minus sign is there, it becomes plus 3 by 2. Can you tell me what is z by z transform of 100 raised to n? Z by z minus 100. What is z transform of 5 raised to n? I'm giving you some time to write z by z minus 5. So now anyway we are going to learn the inverse z transforms. Why not we should write the inverse z transform here only? So here to here, if it is 2 here you write 2 raised to n. If it is 3 here you write 3 raised to n. If it is 3 by 4 you write 3 by 4 raised to n. If it is root 2 here, root 2 raised to n. So that you should remember this structure. You should remember this structure. Shall I write? So here you have to bring this capital Z here and write z inverse, that is z raised to minus 1. So I am writing here the same thing in the reverse pattern. What are the inverse z transform? So I feel that we'll learn some of the inverse simultaneously. This becomes easy. Z inverse of. So we are having fresh memory of whatever Z transform we have learned now. So Z inverse of some 4 to 5. So Z inverse of, okay, Z upon Z minus 2, Z upon Z minus 3, Z upon Z minus 100, Z upon Z minus root 2, Z inverse of Z upon Z plus 6. So inverse means back we should be having n function. Back we should be having n function. If it is 2, 2 raised to n. If it is 3, 3 raised to n. If it is 100, 100 raised to n. If it is root 2 raised to n. If it is plus 6, this becomes Z minus of minus 6. So whatever is there here, that raised to n. So we have done here. So finally this we should never forget. Inverse Z transform of 1 is, of course, 1 raised to n we can write, but it is 1. Or this is also taken as Z transform of n raised to 0. Now as we have seen, the Z transform depends on summation. As we have seen, the Z transform depends on summation. Here there is an important property of Z transform known as linearity property. Just like Fourier transform, Z transform, since summation follows linearity property and Z transform depends on summation, whatever the properties of summations are there, they will be naturally attached to Z transform. Z transforms of some A into Un plus B into Vn minus C into Wn is equal to A into Z transform of first one plus B into Z transform of second one minus C into Z transform of third one. So why not we should do some examples of this. So proof we are skipping here. Why not we should do some examples on the linearity property. Using this function, we can have some examples on linearity property. Have patience. Using this are also important, so that these linearity properties are quite important. So these examples you please practice these examples. Hello, are you there with me? Are you writing what I am writing? See, find the Z transforms. Find the Z transforms of first one. After this we are closing today. These two examples are important, so be careful and attentively listen to this. What is Z transform of 2 raised to n 6n minus 5n square plus something we shall add plus some constant 8. Second one, what is the Z transform of? Find the Z transform of minus 3 raised to n minus 3n cube plus 1. So let us find using linearity property and our previous knowledge Z transform of all of these. So how do you find the solution of this? How do you find solution of this? So first you consider the left hand side. First one. Let us consider the left hand side. Z transform of one minute. Yeah. Are you writing the left hand side of that? Z transform of 2 raised to n plus 6n minus 5n square plus 8. Using linearity property, we should write it is Z transform of first function plus 6 times Z transform of second function minus 5 times Z transform of third function plus 8 times 8, you can write 8 into 1, 8 times Z transform of 1. So this is Z by Z minus 2 plus 6 times what is Z transform of n. So if it is raised to 1, denominator raised to 2, Z by Z minus 1 whole square. So getting used to it every day once you should write what is Z transform of n square. If it is raised to 2, denominator raised to 3. And Z transform of n square, you should remember start from Z square here, n square start from Z square. So 1. So I told you to remember 1, 11, 1, 4, 1, 1, 11, 11, 1. If you remember this much, you can remember Z transform of n square, n cube and n raised to 4. For example, Z transform of n cube is Z cube plus 4Z square plus Z divided by Z minus 1 raised to 4. So this it becomes the Z transform of first three functions plus 8 times Z transform of 1 is well known Z by Z minus 1. So left hand side we had n function, right hand side we have got Z function. So I am coming to the last examples of today's last example. Consider first left hand side whatever is given, whatever the n function is given. So use the linearity property to separate out use the linearity property to separate out Z transform of first term plus Z transform of second term plus Z transform of third term. Z transform of first term minus Z transform of second term plus Z transform of third term. What I wrote? Z transform of first term, Z transform of second term, Z transform of third term. So that is equal to, this is Z by, instead of 2 plus 2 it is minus 2 suppose, then it will be plus 2. So can you tell me, if it is plus 3 raised to n, I would have written minus 3, but here plus 3. Suppose if this is not there, I would have written Z minus 3. Minus 3 times. For Z of n cube, I told to remember 141. For Z of n cube, if you remember 141, so how to write that 141 here? 1 means Z cube plus 4Z square plus Z. So 1, 4, 1 are the coefficients. For n raised to 3, 4. For 3, 4 is the denominator plus Z by Z minus 1. So whatever we have done today, you practice and be ready with again pen and paper, and we shall go ahead with better Z transform and better properties. So today what we did is we found what is meant by Z transform, n domain to Z domain. How we find, because it is discrete, instead of integration we take summation. We started with Z of a raised to n, which is Z upon Z minus a, and afterwards we used a theorem, differentiation, Z transform of n raised to p is minus Z into Z transform of differentiation of Z transform of n raised to p minus 1. Using that n raised to 1, n raised to 2, n raised to 3, n raised to 4, very important. I have told you how to remember. Write down 1 or 2 times. Then we found what is the linearity property. Based on linearity property, some important examples we have done. So we will meet you very soon in the second lecture of Z transform. This is the first lecture of Z transform. Till the second lecture, I take leave from you. I sign off today. Thank you so much. Be with us, be safe, and let others be also safe. Bye.